All right. Well, to begin our first segment today, I'll go back and just do a very brief review of what we were talking about last time, and that was calorimetry, because that's where we're going to begin today with some examples of calorimetry. Calorimetry is a technique where you can measure the amount of energy or heat involved in a reaction, either being taken in or given off, by doing the reaction in a well insulated container. And if the container is sufficiently well insulated, it's effectively cut off from the rest of the universe. And so now you have a universe that's inside a little cup. And you can take advantage of the concept of conservation of energy, because now any energy that's, say, for instance, lost by the reactants will be gained by the surroundings. Normally, the surroundings could be basically anything in the universe, but now we've got our thermally speaking, we've got our universe in that little cup. And so, if the system, that is, the reactant molecules, are giving off energy, then that energy has to be gained by the surroundings. But inside that little cup, the surroundings just consist of any solvent that might be present and the calorimeter itself. And that cuts down the things that have to be accounted for, compared to, say, doing the reaction in a beaker on a desktop, where the desk itself would be part of the surroundings, and the air around the beaker would be part of the surroundings, and so on and so on and so on. So doing it in a calorimeter makes a lot more sense. It makes it much easier to measure the energy involved in a reaction. We saw also the equation for that is the heat basically taken in or given off by a reaction. Heat is Q, and Q equals mc delta T, where m is the mass of the substances involved, and C is the specific heat of the substances involved, and delta T is the change in temperature during the reaction. A lot of times in calorimeters, we will measure the energy involved in a reaction by observing the surroundings. So essentially, we have a thermometer that's stuck into the water in the calorimeter, and whether the temperature goes up or down, that corresponds to whether the surroundings, that is the water, gains or loses energy. So if the temperature goes up, the surroundings have gained energy, but that means the system has lost energy. And if the temperature goes down, that means the surroundings have lost energy, but that means the system has gained energy. So actually, the sign of Q and the sign of delta T will actually be the opposite normally. um, you can use to measure heat transfer during chemical processes, which we'll get to in a moment. But you can also measure heat transfer during purely physical processes, like, for instance, changes in temperature. If you take a hot piece of metal and drop it into a calorimeter full of water, the metal will cool down by transferring heat to the water. The water will warm up from the heat that's being transferred to it, and the two of them, the metal and the water, will eventually end up at the same final temperature. One way, or one purpose for which you can use that technique, would be, for instance, the last example we did last time, to find the specific heat of the metal. And since each metal has its own unique value, well, not totally unique, I guess it depends on how far or how many significant figures you use. But yeah, if you use enough significant figures, each metal would have its own unique value for specific heat. Factoring in a reasonable amount of experimental error, you may not be able to identify the metal individually, but you can at least narrow down what it might be. So finding the specific heat of a metal in order to identify it is one of the things that you can do with calorimetry. Okay, so keep in mind, though, that we're actually measuring the heat that's gained by the water. And since the calorimeter is now, because the calorimeter is thermally insulated, the calorimeter is effectively the universe. And so the total change in energy in the universe is zero, or in other words, energy can be transformed from one type into another, or it can be transferred from one place to another within the universe. but the total amount of energy in the universe doesn't change. And what that means is that within the calorimeter, the energy or heat released by the metal and the energy or heat gained by the water must total up to zero. Another way of thinking of that is that the amount of energy lost by the metal is the same as the energy gained by the water. Only numerically, their signs would be opposite because the metal is losing heat and the water is gaining heat. Since Q, that is heat, is mass times specific heat times change in temperature, mc delta T, we can equalize these two sides here. We know that the negative of the Q released by the metal is equal to the positive of the Q gained by the water. And so if we take negative mc delta T for the metal equals positive mc delta T for the water, we have negative mass of the metal times the specific heat of the metal times the change in temperature of the metal would be equal to the positive of the mass of the water times the specific heat of the water times the change in temperature of the water. So this is just Q of metal, and the right-hand side is just the Q of the H2O. If you want to solve for C of metal, then you just divide both sides by mass of the metal times delta T of the metal, and you get specific heat of the metal is negative mass of H2O times specific heat of H2O times delta T H2O over the mass times the change in temperature for the metal. And this should give you the specific heat of the metal, and then you would be able to compare it to values in the table of specific heats and hopefully decide what the metal is. And some examples of doing this sort of thing come up in the couple of examples we're going to do now. We're not necessarily, in this case, we're not finding the specific heat of the metal. I think there is an example a little later where we do that. But you can also find other stuff. So essentially, you can find anything in these equations. You could find the mass of the metal or the mass of the water. You could find the specific heat of the metal or the specific heat of the water if you really want to, although that's a pretty well-known value, 4.184 joules per gram degree Celsius. You could find the changes in temperature for the copper or the water or both. You could find individual values. Like, for instance, you could find out what was the initial temperature of the metal when you first put it into the water based on how much water there was and what temperature the water started out at and what temperature the water ended up at. And that's actually what's going on here. A 248 gram piece of copper is placed into 390 milliliters of water. Since water has a density of 1 gram per milliliter, that's also 390 grams of water. The water starts at 22.6 degrees Celsius. Remember, the copper is hot, so its temperature is way above 22.6. The final temperature of the water is 39.9 degrees Celsius. Find the initial temperature of the metal, the copper. Okay, first thing to keep in mind, though, is that in cases like this, the final temperature of the water is always the same as the final temperature of the metal, as long as you let the process go to completion. So if you know one final temperature, you know the other final temperature. So we know the final temperature of the water is 39.9, but that's also the final temperature of the copper, and that will help us quite a bit knowing that. And as I mentioned before, 390 milliliters of water is also 390 grams of water. The change in temperature of the water is 39.9 because that's the final temperature of the water, minus 22.6, the temperature where the water started out, and that's 17.3 degrees Celsius for the change in temperature of the water. And we know that this is, again, another case where you're putting a hot piece of metal into water, and so the heat lost by the copper will be the same as the heat gained by the water. In other words, negative Q copper equals plus Q H2O. Q of copper is, well, it's the negative Q of copper, so that's going to be the negative mass of copper times specific heat of copper times change in temperature of the copper. And Q of H2O is the mass of the H2O times specific heat of H2O times the change in temperature of H2O. And then you can just start filling the values in. The mass of the copper is 248 grams, as it said at the beginning of the question. The specific heat of copper is 0.385. No, that doesn't really help. 0.385 joules per gram degree Celsius. You can look that up in the table in the text in this chapter in the textbook. And change in temperature of the copper is going to be final temperature of the copper minus the initial temperature of the copper. We don't know what the initial temperature of the copper is, so we can just write this as final temperature, which is 39.9, minus Ti, or initial temperature of the copper. So just leave it like that for now. And that equals the mass of the H2O, which is 390, times specific heat of H2O, which is 4.184 joules per gram degree Celsius, times the change in temperature of the H2O, which is, again, 39.9 minus 22.6, or 17.3. And over on this side, the left-hand side, we want to solve for Ti of copper. That is the initial temperature of the copper. The first step in that direction would be to get rid of the things that are multiplied by the term that contains the initial temperature of copper. And you can do that by dividing both sides by 248 grams and dividing both sides by 0.385 joules per gram degree Celsius. Okay. And so I've moved those over to the denominator on the right-hand side. And also I've moved the negative sign over to the right-hand side. And so now we just have 39.9 minus initial temperature of copper equals all of this. And it's negative 390 times 4.184 times 17.3 divided by the quantity 248 times 0.385, closed quantity. So you can multiply and divide all this out on the right-hand side, and we come up with negative 295.66 degrees Celsius. And that is equal to, on the left-hand side, 39.9 minus Ti of copper. All right, so you can subtract 39.9 from both sides, and you get negative, remember, this was 39.9 minus the initial temperature of copper. So you still have the negative sign. Negative Ti of copper is equal to negative 295.66 minus 39.9. And that's negative 335.6. And so if the negative initial temperature of copper is negative 335.6, then the initial temperature of copper was positive 335.6. And finally found it. Okay. That was actually relatively easy, believe it or not, because one of the other things you can be asked to do in a question like this would be to find the final temperature. And we know from before that the final temperature for the metal and the water would both be the same. And so you can use the same variable to describe both of them, but then you have two variables. Well, you have two variables in the equation, but they're the same variable, and you're going to have to end up combining them together before you can find out what that variable is equal to. And so we'll look at an example like that. Say a problem very similar to the one we just did, a 248 gram piece of copper starting out at 314 degrees Celsius is placed in 390 milliliters of water at 22.6 degrees Celsius. And our question here is, what is the final temperature? And again, we don't have to specify whether it's the final temperature of the water or the copper, because they will be the same. They'll come to an equilibrium. So remembering that final temperature of copper is equal to the final temperature of the H2O, I'm just going to call that variable TF. And I'm not even going to have to specify whether it's for water or copper, because they're both the same. Okay, so we know that negative the heat lost by copper is equal to positive the heat gained by H2O. So negative Q copper equals positive Q H2O. So that means for Q of copper, that's mass times specific heat times change in temperature for copper. So that's negative mass of copper times specific heat of copper times change in temperature of copper equals positive Q of H2O, which is just mass of H2O times C of H2O times delta T of H2O. And we know all of this stuff except TF. So negative 248 grams times 0.385 joules per gram degree Celsius times delta T for copper is going to be TF, the final temperature, minus the initial temperature, which is 314. And that's going to be equal to the mass of the water, which is 390, because it's 390 milliliters. So water, that means 390 grams, times specific heat of water, which is 4.184 joules per gram degree Celsius, times the temperature change for water, which again will be final minus initial. We don't know the final temperature, but we're calling it TF. And the initial temperature of the water was 22.6. So TF minus 22.6. All right, so you can multiply together the first two terms on each side of the equation. The 248 grams times 0.385 joules per gram degree Celsius lands us on the left-hand side with 95.48 joules per degree Celsius. Notice how grams canceled. And this is still negative on the left-hand side, by the way. And that will be times TF minus 314. But we don't want to multiply that out quite yet. And then on the right-hand side, we can do the same. 390 grams times 4.184 joules per gram degree Celsius gives us 1,631.76 joules per degree Celsius. Notice again, grams cancel. And that will be times TF minus 22.6. Right, well, now probably the easiest way to do this would be multiply through the numerical term over the term that involves TF. So 95.48 times TF minus 95.48 times 314 gives you 95.48 TF minus 29,981 equals, and do the same thing on the other side, 1631.8 times TF minus 1631.76 times 22.6, which is 1631.8 TF minus 36,879. All right, let's see now. What you do then is get the terms that just involve numbers on one side of the equation and terms that involve TF on the other side of the equation. So if we take the negative 95.48 TF over to the right-hand side of the equation, we end up with 1631.8 TF plus 95.48 times TF. And if we take the negative 36,879 on the right-hand side of the equation, move that to the left, the sign changes, so it will now be plus 36,879. Okay, and then taking the negative of the negative is positive, so the 29,981 becomes positive because it's the negative of a negative. And so 29,981 plus 36,879 is 66,770. And that is equal to 1638.1 plus 95.48 times TF, which is 1727.3 TF. Divide both sides by 1727.3, and we get final temperature of 38.7 degrees. And that seems pretty reasonable, especially if you compare it to the example we just did, because you notice the initial temperature of the copper in this example was 314. That was a little bit less than the original temperature of the copper in the previous example. And so we would expect the final temperature of the water and the copper to be a little bit less than it was in the first example. And it is 38.7 versus 39.9, a little bit less, because we were using the same size piece of copper and the same amount of water. So that's why you can compare these two problems directly. You start out at a slightly lower temperature and you end up at a slightly lower temperature. So that makes sense. And then here is, an example, never mind, an example of determining the specific heat of the metal for identification purposes. There's a problem here that says, this is a problem in the book, one of the ones that they don't solve for you. 92.9 piece of anonymous gray metal is heated to 178 degrees Celsius and then immediately immersed in exactly 75 milliliters of water at 24 degrees Celsius. After 5 minutes, the water and the metal have both reached the same temperature, 29.7 degrees Celsius. So find the specific heat of the metal and identify it by comparing the specific heat of the metal to the specific heats listed in the table that's given in the chapter. So we know, again, that the amount of heat lost by the metal is equal to the amount of heat gained by the water. And one of the signs will be negative and one will be positive, for probably accuracy's sake. It would be better to list Q of metal as being negative because the metal is actually the one that's losing the heat. But mathematically, it doesn't really matter. You could use the negative sign on either side. As long as one side is negative and the other side is positive, you're okay. If we're talking about Q of metal and Q of H2O, that means we need MC and delta T for the metal and for the water. So the mass of the metal is 92.9. The C of the metal, that is the specific heat of the metal, we don't know. That's what we're trying to find out. That's the unknown. For delta T, we need final temperature and initial temperature. So for the metal, final temperature was 29.7, and the initial temperature was 178. And it's hard to see there, but I squeezed in the delta T is negative 148.3. For the water, the mass is 75 grams because they said 75 milliliters, and 1 gram per milliliter means that 75 milliliters is 75 grams. Remember, that only works for water, though. For anything else, you'll have to look up the density and do the calculation. For the specific heat of water, that's, again, a well-known value, 1 calorie per gram degree Celsius, but we're using joules here, so that's 4.184 joules per gram degree Celsius. The final temperature of the water is the same as the final temperature of the metal. That's 29.7 degrees. And the initial temperature of the water, it said in the question, was 24.0 degrees Celsius. So delta T of the metal is positive 5.7 degrees Celsius. Okay, so we know that negative Q of metal is equal to positive Q of H2O. So on the metal side, negative M metal times C metal times delta T metal. And on the water side, yes, positive MH2O, CH2O, delta TH2O. So on the metal side, that's negative 92.9 grams times the C of the metal times negative 148.3 degrees Celsius. That's the change in temperature for the metal. On the water side, it's going to be mass of the water, which is 75 grams, times 4.184 joules per gram degree Celsius, times positive 5.7 degrees Celsius. Since the specific heat of the metal is the unknown on the left-hand side, you would divide both sides by everything else on the left-hand side, which would be negative 92.9 grams times negative 148.3. So the negative comes over on the right-hand side, and we end up with specific heat of the metal being equal to negative 75 grams times 4.184 joules per gram degree Celsius times 5.7 degrees Celsius over 92.9 grams times negative 148.3 degrees Celsius. And it's lucky that we have two negatives on the right-hand side because specific heats are always positive. So when you take the negative of the negative, you'll end up with a positive number. And when you multiply all of this out, the specific heat of the metal becomes 0.1298 joules per gram degree Celsius. And that's a little beyond the number of significant figures. Actually, it should be, I guess, three significant figures. So 0.1298 would become 0.130. And in the table, there are two metals that have specific heats, that is, of 0.128. They're not exactly the same as what we found, but they're pretty close. And allowing for some experimental error, they are essentially the same thing as what we found. So our metal could actually be either of those two metals. But notice what the metals are. One is lead and the other is gold. In the introduction to the experiment, it said that the metal is gray. And gold is not gray, it's gold. So if the metal is gray, then it's got to be lead, or Pb, the symbol of lead. So you may not be able to tell exactly which metal you've got just by finding the specific heat, but using that combined with other information, you might be able to identify what metal it is. Even if you can't, you can at least narrow it down quite a bit. Okay, I think that's the end for our first segment. So I will pick up here in the second segment. Using calorimetry for chemical reactions. What we've been doing so far are physical processes, just transfer of heat between a hot object and a cold object. But you can do chemical reactions in calorimeters also, and so that's what we'll start with when we come back.